at some point in your high school geometry career, you probably have heard of your teacher introduce the concept of the law of cosine, which is commonly known as c squared equals a squared plus b squared minus 2ab times the cosine of angle C. Well, how do we actually know this? So let's say that we have some kind of arbitrary triangle that we're going to construct, and we're going to say that from the origin to point P, let's say, is the length A, so that's going to have a verticity at A, comma 0, and let's say we're going to have some other triangle side over here. Let's call that B, and this is going to be P prime, let's say, because we're basically trying to take an obtuse angle line here, and we're going to treat this as if this is revolving around this point here at the origin, and we're going to say we care about this line segment here with PP prime. So, okay, so if all of this is how this is going to be constructed, then we can describe this verticity arbitrarily in the x comma y form as b cosine theta, b sine theta, and that would make the height of this arbitrary right triangle over here. If we drop an altitude, then that's going to have a height of b times sine of theta, and then b cosine theta is going to be the length of the base. So how can we go about this? Well, let's go ahead and write down what I like to call the glorified Pythagorean theorem, which is d equals x1 minus x2 squared plus y1 minus y2 squared. And if you don't know what this is, you can probably find this in your textbook. So now we care about trying to find what c squared is here, and d squared is going to be the distance that we care about here between points P and P prime in triangle P prime O. So squaring this, we're going to have d squared equals x1 minus x2 squared plus y1 minus y2 squared. And now we have to apply this to what we're asking about here, which is trying to find, in this case, the magnitude of P prime. So P prime, and square that. Okay, so now, well, what is our x1? Well, in this particular case, it looks like it's going to be represented by b cosine theta arbitrarily, so that the way that we write this like this is so that it can be true for basically a triangle with any height b at any angle that you revolve. So this is a way to generalize this. And oftentimes, if you can write something in a generalized form, then it can be very useful. So b cosine theta, and our other x coordinate there, or x part of the coordinate is a, square that, plus y1 b sine theta, and we're going to have a y piece of 0, but that doesn't do anything, so we can just cross that out. So now we just multiply this out, so we're going to get b squared cosine squared theta, and then we're going to have 2 pieces inside there of AB cosine theta, and then we have a plus a squared piece plus b sine, b squared sine squared theta, and that looks like it's it. So now we have 2 b squared pieces, looks like, so let's go ahead and just combine the like terms there. So we have b squared times cosine squared of the angle plus sine squared of the angle, but this is something I just talked about in the last video, and we know that this is a very common trigonometric identity, and that just equals 1. So b squared times 1, it's just b squared, so that piece goes away. And then what are we left with? Plus a squared minus the 2ab cosine of the angle. And so now we can clearly see that we end up with a squared plus b squared minus 2ab times cosine of our angle. And in this case, you can say that the angle that we used here, if this is side length A and B, well, this has to be side length C then. And since side length C is across from this angle, that would make our angle have to be angle C in this case by the way that we made the triangle. So yeah, we could even just say put the C in like this, and this is how you come up with the law of cosines to be true. So hope you found that helpful, and stay tuned for the next one where Joe shows you how.